Wow. Good morning, folks.
Steve, do you like notebooks here?
Yes.
What was it?
You're welcome. So, started talking about DMA on Friday. Going to talk some more today. There also, but first, are there any questions on homework 2? Saw a lot of obscure behavior this morning. Particularly disturbing was that many, but not all, earphones destroy the DAC output. It doesn't actually wreck the DAC. It just, the impedance structure of the earphones is such that it makes the output indistinguishable from impulse noise. And so a well-formed sine wave turns into a noise burst. So the answer for this is that if you are going to debug at home, then you either have to use amplified speakers or you have to put a small audio amplifier or impedance buffer on your development board before you plug your earphones in. I didn't know this was happening, and old earphones tended to be lower power. Apparently newer earphones require quite a lot of power. What's the characteristic impedance of an earphone input now? Anybody know? I don't know.
Around 10.
What?
10 to 12.
10 to 12 ohms? Yeah. Oh, well, yeah, of course, then it won't drive it, right? The old electrostatic earphones tended to be more like 200 or 300 ohms, and the DAC would drive that. So you're going to have to put some sort of impedance buffer. It could be as easy as a transistor or an op amp or even an audio amplifier on the output if you intend to debug with earphones. Any questions about Lab 2? I don't know if 2300 has a lab session today. They usually do on Monday, but sometimes they don't. And if they don't, I don't know the TA's name. The instructor doesn't know whether they have a lab or not. So I just have to wait until 1:30 and see if anybody shows up down there. If nobody shows up down there, I'll send out a message saying, lab's open this afternoon, yay! For all you excited people. And otherwise, does anybody want it open tomorrow morning? Yes. Okay. I'll open up tomorrow at 9. 9 to noon tomorrow. Actually, I could probably go 9 to 1 tomorrow, because I just have to be out of there in time for 2300, assuming they come in. Oh, but if they don't come in today, they won't come in tomorrow. You could be in there for 8 straight hours. Oh, baby. That means I'll need a kidney transplant when I go home. Okay. Anything else on Lab 2? Questions on Lab 2? Everything's going okay. Direct digital synthesis is working.
Why did you pick 256 for the side table? Where did that come from?
Why did I pick 256? You know, for the size of it. Well, it turns out that was originally written for an AVR architecture, an 8-bit machine. And so a 256 size array made sense. Also, the shift operator on the AVR was not a barrel shifter, it was a single bit shifter. So if you shifted 24 bits, it took 24 shifts, except that the compiler was smart enough that if you put stuff on a byte boundary, it did a car move from one location to another. So the compiler, the GCC compiler for AVR was so good that as long as you stuck with a byte boundary, you got much better performance. That's the reason I originally did it. The other reason is, if you have 256 points on a cycle, then the first error term is at the 256th harmonic, which is normally above your hearing and way out of band. And if you're stepping slowly through the table, who cares? You still have 256 steps on it. You're just going through more slowly. So the error terms are small and they're far away in frequency, which means they're extremely easy to filter, so it's big enough. There's no particular reason on this architecture why you couldn't go for a 1024 table, for instance, if you wanted to lower the distortion a little bit. I think that there are some hardware DDS units that can be set as high as 12-bit addresses and which clock at 10 gigahertz for doing those demanding RF synthesis applications. But 256 is probably good enough for audio. Any other questions? So Friday I started talking about DMA, direct memory access, and I frankly can't remember where I stopped, but so I'm just going to very quickly review and see if any questions come to mind while I'm doing it. Again, the direct memory access is a separate processor that is of similar status with respect to the system bus as the CPU itself. So there's an instruction port, a data port, and a DMA port, all of which feed into a crossbar. You know what a crossbar switch is? I mean, I've used that terminology, but do you know what it is? Blank? Nothing? Okay. A crossbar switch means that you have some inputs and some outputs, and any combination can be switched together so that you're not looking at a single bus which has one item at a time, but rather a structure that can take several items at a time as long as the target is disjoint. So the instruction port can ask for something from flash memory as long as the data port is reading from data RAM. If you actually read from flash memory like you would with a constant array, then the priority is such that one of these has to take precedence over the other, and I think the instruction master takes precedence over the data port. There are actually 4 channels with an arbitration scheme that then drives the system bus with an address from the direct memory access, which is independent from the data stream and the instruction stream that the CPU is generating. Any questions on that? It's parallel hardware. And again, the terminology is a system event is anything that could generate an interrupt, but for purposes of the DMA, it is not actually an interrupt. It is merely using the interrupt flag. So an event is any system event that can initiate or abort a DMA transfer, which includes any interruptible, any hardware event which generates an interrupt, and probably some software events that generate interrupts. I suspect you could probably generate a DMA burst off of a divide by 0. if you could think up a reason to do that. Transaction is a single word, but a word can be up to 4 bytes. So a transaction could be 1 byte, 2 byte, or 4 byte transfer. A cell transfer is a collection of transactions, and it is the amount of data transferred for one event. A block transfer is all the data transferred when a channel is enabled and consists of 1 or more cell transfers. And the channel stays enabled with a bewildering set of rules. But the basic structure is that it transfers the larger of the source or destination sizes, because when you define a channel, you're going to define an address from which you're going to transmit, an address to which you're going to transmit, the size of the transmit block, the size of the receive block, and the size of a cell transfer. Oh my gosh. But if auto enable is turned on, the block transfer just repeats forever. And if you manually disable a channel, then until you enable it again, nothing happens. And I think I talked about the basic operating modes. Did I do this last Friday? It's beginning to run together. I did, okay. You can transfer, you can copy memory to memory, including I/O. You can do a cyclic redundancy check. You can do a pattern match. You can chain channels, if only you can figure out what that means. And you can combine all those. And I think I think where I left off was a cell transfer can be initiated in 2 ways. You can use software to initiate a cell transfer, but that's a bad idea. Because if you're using software to initiate a cell transfer, it means that you're saying, okay, send a byte. If you're going to do that, why not just copy the byte in software? So initiating a cell transfer by software is a bad idea and a waste of time. However, it does make sense to initiate a block transfer, because now you can take an arbitrarily long string and say send, and then go back to whatever you're doing, and the DMA channel will barf it from one memory location to another. And maybe I'll just show you an example of that. So we're going to go to the proto-threads header code, where I use this for... We're going to go to the proto-threads header code. There we go. And let's go down to the bottom where we actually set up the DMA channel. And because you can think of the DMA channel as a general purpose controller in many ways, it is not simple to set up. There's a ton of stuff you have to do. The first thing we did, though, I'm using the DMA here to send a string out of the UART port. So first you have to set up the UART. You have to tell it what the transmit and the receive pins are for the UART. You've got to configure the baud rate and the TX and RX pins. You got to give it a baud rate. You got to tell it the data size is 8 bits. You got to do all kinds of stuff. We're going to ignore that for right now. The main thing we want to talk about here is you're going to do a DMA channel open. We're going to send this UART data from memory to the UART on channel 1 at priority 2, and we're going to open the DMA in match mode. To open in match mode means that we're asking the DMA channel in hardware to do a data comparison and to stop when it sees a match. And the match we're going to go on is hex 00, which is the ASCII end of string. It's the C end of string. So we're configuring the channel to stop on the end of string. We're going to set the event control. What event are we going to trigger on here? Well, we want to send a new sending characters is quite slow on the UART. At 9600 baud, each character takes, coming out of the serial port, takes 1 millisecond. So 40,000 cycles. It's forever on the CPU scale. We don't want to have to wait for that to happen. So we're going to set up an event which says, when the UART signals that it's empty, send another character in hardware. No interrupt service routine, no software involved once we turn this on. So we're going to enable the transfer to be automatic once it's started. And by the way, that is exactly what you're going to be doing for Lab 3. Is once you start the transfer, you're going to send the whole block, but in your case, the event is going to be a timer event, not a UART empty event. So, set event control, again, timer channel 1. We're going to give it a event for a start interrupt enable. We're going to tell it that the event also, the match enable event is turned on. That's for stopping the channel. And then the start event is the interrupt corresponding to the UART2 empty. Let me unzoom that a little bit, zoom out a little bit so we can see that. It's the UART2 TXIRQ, which means that there's space in the transmit buffer for the next character. Okay, so then we have to set up the transfer locations. So what we're going to do here then is say that for channel 1, we're going to go from the location in memory, which is the address of the send buffer string, and we're not starting at the first character but rather the second character. So this is the name of a variable I've chosen. This is the name of a variable, PT send buffer, and I'm starting at the first position rather than the 0th position, because to prime the pump to get the UART to send the first character, we do that manually. So we send one character, and then when the UART empties, boink, the DMA fires off the next character with no other software. The target, so this is the send location, the array location of the send. This is the location of the receive, which is the address of the symbol UART TX register, the transmit register. The maximum number of characters we can send is given by the macro max cars, which I set to be, I don't know, 64. But remember, we'll never actually send that many because the transfer will stop when we get to the end of string marker, the 0, 0. That's the length of the source. The target length, which is UART TX reg, is 1 byte. So we're going to send n bytes from the location of PT send buff to UART, which is of length 1. So we're going to send it over and over again to the same location, which is what you mean by an output register. And on each cell transfer, on each event, remember the event here is the TX empty event. On every TX empty event, we're going to send exactly 1 character, 1 byte. Now, it turns out that I wanted to set up PT threads, proto threads, so that when you asked to print a string, it would send the first character, enable the DMA channel, and then do a context switch and just wait until the channel said it was done. So the next line does an event enable flag so that the channel can output a block done command, a block done signal. So this is now an instruction to the DMA channel itself to send out an event, which is going to be the block done event. Oh, so. And then, last but certainly not least, we have to set up the match pattern. What do we want the data to match on? We want it to match on hex 00, which is end of string.
This is a question about the transfer setup. I guess about the terms that you were using before. You said that the channel is disabled when when the smaller of source and destination size has been transferred. Here your destination size is 1.
No, it's the greater of. Did I say lesser than? Lesser of?
I don't remember.
I mean, it's greater of, when the greater of. So it's going to iterate across this array, the array that starts here, and until it gets to the, in this case, the channel match pattern. So now we've programmed the channel. So at this point, the channel is all set up and ready to go, but it's not doing anything because it's not enabled. It's just sitting there waiting for the data. It knows its source, it knows its destination, it knows its pattern, it's just waiting. So now we go back up to the DMA send string. So this is PT DMA put serial buffer. It's meant to be spawned as a thread. The first thing it does is make sure that the foolish user has not sent a null string. So it makes sure that the first buffer entry, PT send buffer 0, is not 0. If it's 0, it just exits. And it can exit here because you're exiting back to another thread. This is a spawned thread. Then we yield until the UART transmitter is ready. Why do we do that? Well, we don't want a block waiting for the transmitter to be ready. And remember, there could have been another thread which sent a string. The thread then exited, but the string is still being sent because it took a whole millisecond to send the last character. So this waits until the transmitter is actually empty. But it's not a blocking wait. It just relinquishes control back to the threader. Then we do a UART send data byte, and we know this doesn't block because the transmitter is ready. So PT yield does not block because it's a thread yield to another thread. UART send byte does not block because the transmitter is ready. The very next thing we do is a DMA channel enable channel 1. As soon as we send that command, the channel takes over the transfer and does the rest. It was all set up, it was primed and ready to go, now it's running. Then all we have to do is wait until it's done. So we're going to do a wait until DMA channel get event flags, channel 1 and DMA event block done. So that the signal that the channel is sending is going to be received by this wait yield until, which is also not blocking. So the whole time that the string is being sent, remember a string can be rather long, it could be a couple of hundred characters, but is more likely to be 30 or 40 characters. For that 30 or 40 milliseconds, instead of wasting it, waiting for the timer, waiting for the string to be sent, the threader goes off and does something else until until the yield until the yield is satisfied. Then it comes back, and then, and this was the one thing that is different between PT threads 1.2 and 1.2.1, was that there was an error in that I did not wait until the UART was completely empty, until the FIFO was completely empty, which could be many milliseconds later. And as a result, some number of characters were being corrupted or lost. So no matter how long the string is, the only thing that sends it is the DMA channel enable. The DNA channel runs until the compare match, and then is disabled until the next DMA enable. So you send exactly one string, the compare match disables its own channel, and you just wait until the user wants to send another string. Questions? Yes?
Can you have multiple channels running at the same time?
You can have up to 4 channels running at the same time.
Do they slow each other down?
They do slow each other down. The channels slow each other down because they are one address source multiplexed between 4 channels. You get to set the priority of the channels. But if they have equal priority, it's round robin. You go through the list of channels and it starts over again.
Can you explain the PT yield with the bitwise and in it?
This thing?
No, the one above it. Like, what are the two things and there mean?
So this returns a bit mask of all of the events that are true in channel 1, and the event block here is the specific the bit for the specific event.
So this is effectively waiting until DMA signals that it's done with it.
This is waiting until the DMA signals that it is done. So between these two, you start it, then you just yield, you go off and do whatever else you want to do until the DMA is done, then come back. In terms of the threader, it's very efficient because you're not having to do a per character context switch or anything of the sort. You're doing a per string context switch. In the case of Lab 3, what you're going to be doing is setting up, instead of a target which is the UART, you're going to be using a target which is, I think it's called CVCON. It's going to be a 1-byte register that controls the onboard Vref DAC, and the source is going to be an array of samples representing whatever audio signal you want to put out. So you'll set up the DMA transfer in main once for the start sound, another source for the target sound, another source for the end of game sound, so it could be 3 DMA channels, or you could actually change the source on the fly. And all 3 channels are just going to sit there doing nothing until the software says, send the whole array. And then the DMA channel will barf the array out to CVCON. taking no CPU time, so you get better execution time and therefore a higher grade. Oh, sorry, CVCON. Okay. So any questions on that? You can stop a DMA transfer by manually writing a channel abort command, by a pattern match as we've just beat to death, an interrupt event that matches the selected channel abort event source. So just as you can start a channel on any hardware event, you can stop a channel on any hardware event. Detection of an address error. I've been trying to figure out how to generate an address error. I guess you could try and you could probably try and use a source that's past the end of memory. I don't know. I haven't yet generated a address error. Has anybody managed to do that?
About 0.
0, good question. I don't know what happens at 0. 0 would be probably the interrupt vector table, which might be interesting to read out, but I don't know what would happen in terms of an interrupt. Or a block transfer completes when auto enable is not on. But you can also then generate interrupts from the DMA, or in general events. You don't actually have to generate the interrupt, but you can generate events which can cause an interrupt. There's various error interrupts, there's abort interrupts. If something stops the transfer, the channel itself will throw an interrupt saying, I stopped. Block complete interrupts, cell complete interrupts. A cell complete interrupt doesn't seem like a good idea unless the cell is rather long, because that could use up a lot of CPU time. And a couple of other channel control things. So one of the very first things I tried to do is to see how fast I could run a DAC. And the DAC I was using in this case was an R2R ladder. Do you know what that is? An R2R ladder DAC? It's a passive parallel DAC. Let me see if I happen to have a picture of that handy. I didn't include the data sheet. How sad. Okay. So the R2R DAC is going to take a data word, and I only had I used just 6 bits here, I think, and so I'm spitting 6 bits out to port B. So the actual target is, I can never draw an ampersand. I'm not used to, we'll just do ampersand LATB, which is the output register for port B. And so when we set up the transfer, I'm just going to barf a memory block to the output port. And one way of, this was partly by way of trying to figure out how fast I could make it go, which was about 3.2 megasamples per second, because it's 1 byte samples. But the channel control is somewhat easier than with the full pattern match thread deal. We're going to open a channel, and we're going to put it in auto mode, which means it never stops. It's in auto enable mode. Then we're going to do a DMA set transfer from a sign table, a DMA set transfer from a sign table to the output port, which is lat B. The size of the transfer is going to be the sign table size as input. 1 byte is output because we're outputting a 1 byte number to the B output port, and the cell transfer size is 1 byte. You will note that this is not direct digital synthesis, but rather, because I was using DMA here, to change the frequency, I changed the frequency of the sampling rather than the increment of a DDS variable. I was doing this to get maximum high frequency performance but that sacrifices frequency setability. So this is not very settable. You can't choose any arbitrary frequency, but the frequency you choose can be quite high, up above 100 kilohertz. So this method is not acceptable for Lab 2, but in Lab 3 I'm not asking for a precision frequency. I'm merely asking that you make 3 sounds that are unique and different from one another. Honk, squeak, and tweet. You know, whatever. The event control is that we are going to do a start on the timer 2 interrupt. That means that every time timer 2 does a compare match, that we do 1 cell transfer, which in this case is 1 byte. This is very much like what you're going to do for Lab 3. Then we enable the channel, and once we do that, it starts spitting out data forever because it's in auto enable mode. So this generates a sine wave forever. The operational definition of forever is longer than 1 lab period. Unless you're a faculty member, and then it's longer than the time it takes to get tenure. Then we just do a little bit of bookkeeping. We set up a bunch of bits to be outputs and do some zeroing and get ready to send stuff to port B. But the main thing is to set up a source, a destination, a size, a trigger source, in this case timer 2, and enable the channel. And then it just produces sound forever. So, for instance, if you wanted to, for Lab 3, if you wanted to have the background music from Tetris playing indefinitely, to see if you could mess with the sanity of the TAs, then you could run a table that just loops forever with no CPU. Once you've done the setup, once you've done the DMA setup stuff, then starting the DMA channel is either done in hardware through timer 2, or in the case of the print code, you do the DMA enable, which is a 1 byte transfer into a control structure, and then the whole block is transferred out with no CPU. No CPU. questions? So then you start looking at the channel and reading the documentation very carefully and saying, what else could we do with this thing? Something that reads and writes memory, could it be a computer? Could it actually be another CPU for which you could write a compiler, however twisted that might be? And the answer is yes. You can use chained DMA channels as a Turing machine. It's fairly painful. I don't suggest doing it for a final project. I think it's too hard for this course. But it's an interesting concept. Because then you could make a 5-way parallel machine running on the one die. Right, 4 DMA channels plus the CPU could all be executing their own instruction streams, however twisted that might be. But for now, whenever you think data motion, think DMA. For instance, you do a screen clear. That could be a DMA operation. If you're writing all zeros to a block, let's say you want to do a mem clear or a mem copy. If you ever use the keyword mem copy, you're just doing a software version that could be replaced with a DMA burst and take 0 CPU time. There are, however, some synchronization issues. If you start a mem copy, you know that mem copy doesn't return until all the bytes are copied. If you start a DMA transfer, it finishes sometime later. And whatever you do in the meantime, before it finishes, better not depend upon the results of the copy.
PLib has a blocking mem copy implemented in DMA.
Of course it does. Okay, so PLib has a blocking mem copy in DMA. So if it's a blocking mem copy, what's the point? If it takes the same length of time? Oh, maybe it's faster. I'll bet it's faster because, yes, because since mem copy is faster as a DMA event because you don't have to do the interpretation, the read a byte, write a byte, read a byte, write a byte, because the hardware does it all in parallel. So it probably is a factor of 2 or 3 faster.
It doesn't have to do bounds checking either.
It doesn't have to do bounds because it's doing the bounds checking in hardware, right? So probably 3 or 4 times, 2 to 4 times faster. Any questions? The hardest part of this, it seems, is wrapping your head around the idea that the CPU is not in charge, that there's a separate processor involved, and that you don't have to deal with every byte separately, but you can let hardware do it. And that seems to jam some people up so badly that they would rather write an interrupt service routine to send data rather than figure out how to set up the DMA. And that's a gross waste of time, of CPU time. Final projects. And no questions? Let's talk about final projects. Any questions? It is now a little over 2 weeks until you need to tell us what you're going to build. And so any thoughts on this? So last year's projects, in no particular order. I link up projects in the order they're sent to me. First one was shaft vibration analysis. This was a rather high-level replacement of a piece of hardware in a mechanical engineering lab by a student who is a mechanical engineering student and was outraged by the fact that one of the pieces of hardware they had to use in the lab cost $20,000, and it was basically two A to D converters and a phase meter. So he redid it for about 50 bucks, and there were a few cute things about it. For instance, he used a laser cutter to I didn't know you could do this. First of all, to cut the wood panel for the front piece, that I knew you could do. But then he used the laser cutter in low power as a wood burner to write letters on it. Very cool. FIR filter design. This group did a a program that ran on a touch screen that allowed you to lay out the pass characteristics of an FIR filter, finite impulse response filter. Then it ran Parks-McClellan algorithm on the PIC32 to find the best fit, where the best fit is the minimum, it's not least squares, it's maximum error fit, and then run it against audio on once it was designed, it could run it against an audio signal on the chip itself. Wireless biometric pen drive. There's a little box. It had in it a wireless charger, so you could set the box on the charger and it would charge up the LiPo battery inside the box. It had wireless data transfer. It had a thumbprint reader. It had a OLED screen for reading out the status of the thing, and it had an SD card. So you run your thumbprint against it, put it down near your computer, and it reads by, I think it was Bluetooth, into the read data by Bluetooth across to a laptop. GPS navigation for runners. It was a device that you put on your arm, and it gave you some cues about how to turn and how to navigate. Capacitive touch piano. It turns out that you can set this thing up to, you can set up the chip to do touch detection on 30 or 40 channels. So he made this was very pretty. This was a pretty project. Let me see if I can get a picture of the device. It was a really nice looking piano, and using aluminum and then copper strips for the black keys. And since the student could actually play the piano, he could demonstrate it very nicely. Glove piano, glove keyboard typing, glove sketch. Gloves are big. iClicker to cell phone interface. This caused some soul searching because this reverse engineered the iClicker protocol, which could be a violation of the Digital Millennium Copyright Act. You're familiar with that? DMCA? And after thinking about it for a while, we decided it probably wasn't, because it wasn't designed to spoof iClicker, but rather to reverse engineer and enhance it. But it's an interesting ethical question. Wake you up. Oh, please, not that. Alarm clock. At various times, people have designed alarm clocks that fit their personality in various ways. Lights that faded on, alarm clocks that jumped out of your way. One of them, you had to reach up to grab it, and every time you grabbed it to hit the snooze alarm, it went up another foot. Alarm clocks that screamed at you in your mother's voice. You name it. Always fun. All right, I'm going to go see if the lab's going to be open at 1:30. I can't promise anything, but if it's going to be, I will bounce an email out in the next half an hour.